Hello everyone, Mitchell here, and today I'm going to be conducting my final review for the upcoming exam this Tuesday. I solicited some some topics that you all were most confused about before the exam. I'm going to be using this list here to make up my review. I'm going to cover this in no particular order. Let's go ahead and start off with greedy algorithms. So greedy algorithms um, basically take the most immediate optimal step without making any long-term considerations. Um, let's go ahead and find the shortest path from A to F using a greedy algorithm, and let's demonstrate that now. So starting off at A, you can see it has two neighboring nodes, B and C, and we're going to go ahead and go to visit C next since 6 is less than 13. And then considering the nodes of C, we can see the lowest weight is B, so then we're going to visit that node next. And considering the non-visited nodes of B, and then the neighbors of C, we can see that 1 is less than 8 here. So we're gonna go ahead and visit D. Now that we're at D, we're adjacent to F, and it does have the lowest weight as well. So we're gonna visit F. We found the path from A to F. So although it will always produce a correct output to the problem. This isn't optimal because the path to A to F through E actually has a lower cost. So let's see here. So it's 6 plus 8 should be 14 plus 2, which is 16. So we can see there actually is a shorter path. So greedy algorithms will not always find the most optimal path, but they will find a correct answer. And since the algorithms are generally simple, they have minimal time and space complexity, which is an advantage of the greedy algorithms. Um, so let's talk about the big O notation here. Um, so even though you can see it took there's 1, 2, 3, 4, so it took 4 iterations. Um, the big O for this operation is n, which is just the amount of nodes or vertices. Um, because in the worst case, it when you want to find the path from one node to another, it'll have to explore every other node before it gets the last node. And we also want to always remember that big O, you want to consider the worst case scenario. All right, so dynamic programming is a way to solve a generally complex problem by dividing it into overlapping subproblems and then compiling all of the solutions to the subproblems into one final solution for the entire problem. So now I'm going to show you 3 different dynamic programming algorithms on that graph that we just saw. So let's go and start with Kruskal's. So this is an algorithm to find the minimum spanning tree, which is a path through um, a graph with a minimal total cost, and it also visits every single node. So I have the description here of the algorithm from Geeks for Geeks. I included the link here if you want to learn more. Otherwise, you can just Google it. So here are the steps. So we're going to sort all the edges in non-decreasing order of their weight. And then we're going to pick the smallest edge, check if it forms a cycle with the spanning tree formed so far. If cycle is not formed, then we can include the edge, otherwise discard it. And step 3 is to repeat step 2 until there are v minus 1 edges in the spanning tree. And then I added this little part here, and just to kind of describe what a cycle is, and that's when there are there's more than one path from any one node to another node. So in any true minimum spanning tree, that there only should be one way to traverse from any node to any other node. There shouldn't be I guess say options. There shouldn't be multiple paths. And I'm gonna go ahead and demonstrate this in um, using this graph. Using this graph. So let's go ahead and get started. So you can see there's 12 vertices here. So the minimum spanning tree is going to have 11 edges. So right now we're at 0. And then I went ahead and put out all the weights here and sorted them just to save time. Fortunately here, all of the weights are unique, so I'm able to identify the edge with the weights. But if you're doing this problem on a test and there are duplicate edges, you would want to just identify each of these weights using a key, which would be like B to C or A to C. And then to break ties, I would just use alphabetical order if there are identical weights. However, I don't think it matters which way you break ties. So let's go ahead and get started. So we're gonna want to pick the lowest weight here, and the way also you can represent this is using a min heap, right? Which gives us readily available access to the minimum value in the list, or you can sort it, which is how I've done here. Both work. So now that we're at 1, we can go ahead and add this to the list, and you can see it doesn't create a cycle because there's nothing to create a cycle with just yet. Let's keep moving. So then we take the next lowest, oops, slow down. Okay, so now we get the next lowest weight, which is from F to E, and then we could go ahead and add that to the list, the list of edges in the spanning tree, which I've just represented by this yellow highlight here. And the next one is 3. So this, again, this doesn't create a cycle because we don't have much here quite yet. 4, that's good, doesn't create a cycle because those two nodes weren't previously connected. There we go, we can add 5, and then 6, that's good. Going to 7. So the way you want to tell if it creates a cycle or not is, so we see C and B here. Right now there is no way to reach B from C and vice versa. So that way we can go ahead and add that edge there, since there's no pre-existing, like not necessarily like pre-existing through this edge, but pre-existing through like another route. So if 13 had already been connected, then adding an edge here would create a cycle. But we keep going here, I'll show you what I mean. So we can add that edge, and then consider this edge, which is the next lowest weight. You see we don't want to add a cycle here because if we're at C, we can go to C, B, D, F, and E. We can already reach E from C. So adding the 8 edge to the minimum spanning tree would create a cycle, and it's pretty intuitive here. You can see that there's just a circle in this case, so we don't want to add that. We're going to discard that edge, and then we're going to move on to 9, and then of course you can see this creates another circle here. We don't want to add this either because it creates a cycle, and let's consider 10 here. 10, you can't reach K from G, so let's go ahead and add 10. So now we're at 8 out of 11 edges. We're almost there. Let's keep it up. Now considering 11, so you can already reach K from I, so you just need to traverse from I to G to K, so we don't need to add that edge there. We're going to discard it. Now let's go ahead and consider the edge 12, which is right here. It looks like we can add that because there's no way to get from L to K yet. So, yep, looks like we're going to add that edge. We have 9 out of 11 edges. So let's consider the edge 13 here. Where is it? Why is it taking me so long to find it? Oh, yeah, right up there. So yeah, we want to discard this as well because again, this would just create a loop here, and can already access B via C. So we're going to discard that edge. And then if we're considering 14, again, this creates another cycle, so we want to discard it. And then let's go ahead and add 15 here. It looks like there's no way to reach H here, so we need to add that edge. And again, we can discard this because it doesn't add any new nodes, and that creates a cycle. Now 17, that creates another cycle. You can see we can already reach J from H going through. We can go to H to G to K to L to J. So we don't need to add this H to J there. Now finally, we can just add the edge here. That is 18, since that is the next minimum edge. And since we have 11 out of 11 edges, we know that we have our minimum spanning tree here. And you can do a few things, just confirm that it's right. Minimum spanning tree should definitely visit every node. And then you can also just study it and see if there's any shorter total distances between them all. But it looks good, so that's how you use that algorithm type for creating minimum spanning trees. Now I'm gonna go ahead and show you how to use prims, which works a little bit different. So let's see here. So it says first create a set, MST set, that keeps track of all vertices already included in MST. Assign a key value to all vertices in the input graph. Initialize all key values as infinite. Assign key values as 0 for the first vertex so that it is picked first. While MST set doesn't include all vectors, we want to loop. And we're going to pick a vertex U which is not there in MST set as a minimum key value, which usually use a queue, which uses a min heap representation. Then we want to include U into the set. And then we're going to update the key values of all the adjacent vertices, where the weight is less than the existing key value. Otherwise, we don't need to update it. So that's how the algorithm works. We're going to go ahead and do the exact same thing on this graph. So here's basically the min heap or the queue, which allows us to, if we use a priority queue, it allows us to get the node with the lowest weight, using a complexity of only 1. So you can see I followed the first step. I set all of the I set all of the weights to infinite, besides the first vertex, and you can pick any vertex here. It's arbitrary first vertex. I just chose A because it's in chronological order. So let's go ahead and get started using this algorithm. So we're gonna go ahead and visit A and consider its neighbors. So we see B has a weight of 13 and C has a weight of 6. So both of those are less than infinity. So we can update both of those. So we're gonna set the key of B to 13 as well as the key of C to 6. Now we want to go ahead and the next node we're gonna explore is C, because it has a weight of 6. Now we consider the neighbors. So B has a weight of 7, which is less than 13, so we're gonna update that. And then 14 is less than infinity, so we're gonna update that as well. And 8 is also less than infinity, so we're going to update both B, D, and E. As well as H here, because 20 is also less than infinity. So we have the weight for H set to 20, the weight for E set to 8, the weight for D set to 14, and the weight for B is set to 7. Which now we have this, we want to select which we're going to explore next. And so this 0 and 6 would be the lowest. However, we want to explore whatever is not already in the set. So the next lowest would be B, right? Let's go ahead and consider B. Then we would just need to go ahead and update D, because that would be 1 is obviously less than 14, and then we would explore D next. Okay, great. So we update D to 1, and then since this is 1 is lower than 8 and 20 and infinity, we're going to go ahead and explore D next. If we consider the neighbors, so we have a weight of 9 and 3. So 3 is less than infinity, so we're going to update that. And then 9 is 9 is not less than 8, so we're not going to update it. So you can see I went ahead and updated this here, but E remains to be 8. So now if we consider this priority queue, we can see that the lowest key that it's not already in the set is F. So we're gonna go ahead and explore that next. And then the only neighbor that we need to update for F is E, and E is 8, so we can go ahead and update that to 2. And that is what we did. And then the only neighbor we now need to consider is J. So we can go ahead and update, once we're at E, we can update the path of J, or update the weight of J here to 18. So let's go ahead and do that as well. Now, the only node here, well, not the only node, we actually have 2. We have H and J is obviously lower at 18. So once we get to J, we're going to have a few nodes to update. We're going to have H, which we can update to 17, K, which we can update to 16, and L, which we can update to 4. So let's go ahead and do that. Oh yeah, as well as G. Let's go and go back one. Yeah, so update G since 19 is less than infinity. All right, so we updated all of the neighbor weights. It looks like the next lowest one is going to be L at 4. So let's explore L. If we consider L, it just has one adjacent node we need to worry about, which is K. And 12 is less than 16, so we're going to update the weight of K to 12, like so. And then since 12 is less than 19 and 17, we're going to explore K next. If we consider its neighbors, G, we have G with a weight of 10, so we're going to update G from 19 to 10. And then we're going to update I from infinity to 11. So let's do that. Alright, looks good. So we just have 3 nodes left. We're almost done. If we consider the smallest one, it looks like G is obviously the smallest one, so we're going to explore that next. If we consider its neighbors, we have I, which has a weight of 5, which is less than 11, so we're going to update 11 to 5. And then 15, which is less than 17, so we're going to update 17 to 15. Alright, great. So we completed this Prim's implementation of minimum spanning tree. Looks like this is right. This is the same minimum spanning tree we got in the last implementation, and it looks correct. Everything's connected, and we have seemingly optimal paths. This is a dynamic programming problem since there are subproblems, which the solutions are saved for future use. We can see, for example, a subproblem would be what is the lowest edge weight of adjacent neighbors from J, and then that would be the same problem for any node here, and that would be the collection of subproblems. So let's go ahead and talk about Dijkstras. If Dijkstras, I think that's how you pronounce it, but this is another dynamic programming algorithm. So the way it works is it's really similar to Prim's, however there's one big difference, and that's for every adjacent vertex v, if sum of distance value of u from the source and weight of edge u v is less than the distance value of v, then we want to update it. So otherwise it's super similar. Again, I have the link here, otherwise you can Google it and read more about it. But I'm going to go ahead and show you how it's implemented on this graph. And let's go ahead and start with A since it's for consistency's sake. and since it's the first chronologically. So we're gonna go ahead and say A to 0, so we can find the shortest path from A to every other node. And this is again a priority queue, since we're gonna want to pop off the lowest key here. We're gonna want to access it easily, be able to access it easily. So after we explore A, we can see we can update the weights of B and C to 13 and 16, so both less than infinity. And then since we're gonna want to go ahead and consider C next, since 6 is less than 13. And then if we consider the adjacent nodes of C, what's going to be different here compared to Prim's is that we're going to want to take the distance of C to the adjacent nodes and then add them up and then consider that. So you can see the distance to C is 6. So the distance to H is going to be 6 plus 20, so it's going to be 26. So 26 is definitely less than infinity. And it's the same thing in all of these cases here. So it's going to be 6 plus 8, 6 plus 14, as well as 6 plus 7. So we don't want to update, we don't need to update B because 6 plus 7 is 13. And that's the value that already exists. So yep, looks like, so I just went ahead and updated them all here. Okay, so we have all of these, looks like all of these values were updated accordingly. Again, we don't need to update B since it's already 13. If we consider the next lowest weight, we can see B is obviously the lowest one, so we'll explore that next. And then the only neighbor we would then need to explore is D. So we would then update the weight of D from 20 to 1 after that. Oh, excuse me, sorry. It'd be the weight of the distance to B plus the weight of the edge. So the distance of B is 13 plus the weight of the edge would be 14. Now, looks like we have a tie here. I'm just gonna break it alphabetically, so D would be first. Now, if we consider the neighbors of D, distance to D is 14, and the distance to F is 3, so then we'd update F to 17, and then 9, which is the weight from D to E, 9 plus 14 would be 23, which certainly is not less than 14, so we're not going to update E, which we can see in this next slide. So the next lowest distance will now be E, which is 14. So we're going to explore that next. If we consider the neighbors, we have F, which will be 14 plus 2, which will be 16. So 16 is lower than 17, so we're going to update F to 16. And then it looks like we can update J as well. So 18 plus 14 is 32, so we're going to update J to 32. Let's do that now. Alright, looks like F is now 16, J is now 32. And if we look at this list, the next lowest distance is F, so we're going to explore that next. And F does not have any neighbors we need to consider, so we're not going to update any distances after that. Okay, so this isn't supposed to be highlighted. It looks like it just came over from the previous slide, but that's okay. So the next edge we need to consider is H, because 26 is lower than 32. So if we consider now H, the neighbors of, no, we're definitely going to explore H, never mind. Okay, so we have all of these, looks like all of these values were updated accordingly. Again, we don't need to update B since it's already 13. If we consider the next lowest weight, we can see B is obviously the lowest one, so we'll explore that next. And then the only neighbor we would then need to explore is D. So we would then update the weight of D from 20 to 1 after that. Oh, excuse me. Sorry. It'd be the weight of the weight the distance to B plus the weight of the edge. So the distance of B is 13 plus the weight of the edge would be 14. Now, looks like we have a tie here. I'm just gonna break it alphabetically, so D would be first. Now, if we consider the neighbors of D, distance to D is 14, and the distance to F is 3, so then we'd update F to 17, and then 9, which is the weight from D to E, 9 plus 14 would be 23, which certainly is not less than 14, so we're not going to update E, which we can see in this next slide. So the next lowest distance will now be E, which is 14. So we're going to explore that next. If we consider the neighbors, we have F, which will be 14 plus 2, which will be 16. So 16 is lower than 17, so we're going to update F to 16. And then it looks like we can update J as well. So 18 plus 14 is 32, so we're going to update J to 32. Let's do that now. Alright, looks like F is now 16, J is now 32. And if we look at this list, the next lowest distance is F, so we're going to explore that next. Alright, so we can now see we don't need to make any updates in F since there are no neighbors that are not already in the set. If we look at the priority queue here, we can see that the lowest node to be visited is H. So let's go and explore that next. We consider its neighbors, G and J. Those are still set to G is set to infinity, so we'll need to update that, which will be the path of H plus 15, which will be 41 to G. And then J, that would be 26 plus 17, which is certainly not less than 32, so we're not going to be updating J. So we're just going to be updating G. As you can see, yeah. Alright, so we can now see G is updated to 41, and then J is still 32. And if we consider the nodes here, the lowest is 32, because 32 is less than 41, so we're going to explore J next. We consider the neighbors of J, we're going to need to update L, because that's still infinity, as well as K, and so path is to J is 32. 32 plus 19, that'd be 51. 51 is certainly not smaller than 41, so we're not going to update G. We're just going to update K and L. So let's go ahead and do that now. Looks right, so 32 plus 16, that's 48. And 32 plus the 4 here, that's 36. We have those updated. Alright, so if we look at this priority queue here, we can look at these values here and see that L is the lowest value, so we're going to want to go ahead and explore that next. We consider the neighbors. We just have K to worry about, and so the distance to L is 36 plus 12, which should be 48, so that's the same as the cost from J to K, so we can go ahead and select either of those here, since they both equal 48. Let's go ahead and step through. I'm pretty sure although this is 48, it looks like we still have a lower path cost here of G for 41, so we're going to explore that first. If we consider the neighbors, we just need to worry about k and I. So the cost to g is 41, so the cost to k from g would be 51, which is not less than 48, so we can keep that. And then it looks like I is infinity, so that would be a total cost of 56. We can update I to 56. Sorry, 46. We can update I to 46. And then it looks like we're going to explore that next, since 46 is less than 48. So yeah, let's go ahead and see, and then we're going to explore I. And then last but not least, we just have k left. So, and yes, we don't need to update k because the path cost to I is 46. Plus 11, which would be 57. 57 is still more than 48. So we're going to explore k. We can either do from j or from l. But we're going to go ahead and do l. And that looks good, since this set here is now full. It has all the nodes in it. We can go ahead and stop. And this is the shortest path graph from A to every other node here. So it looks good. Also, all the other nodes are connected. Okay, so that concludes my review for the final exam. I wish you all the best of luck, not only for this final exam and your other final exams, but for the rest of your academic career here at ASU. Thank you for taking this course, and thank you for having me as your TA and letting me help you all. It was a great experience. You know, they say the best way to learn is to teach. And I learned a whole lot through this semester, as I'm sure you did as well. I will be making one other video, which will be how to find an internship, which I'm sure you all will find very useful. Once again, my name is Mitchell Bucklew. I'm your undergraduate TA, and thanks for watching.